This is section 7.8 on improper integrals. So there's a definition, part A, part B, and part C. For part A, if you have an improper integral with the limit of a constant and then the upper limit is infinity, then you can rewrite the integral as a limit. Part B, if the upper limit is a constant and the lower limit is negative infinity, then you can write the integral as a limit as well. And we're trying to determine whether these integrals are convergent or divergent, which means that the limit does not exist. And you can also have infinity on both ends, which means that you can break up the integral into two separate integrals with the constant a being any number that you choose, any real number. This little theorem is also very important. It comes in very handy for some of these problems, a lot of the problems. It just says that if you have something of the form of 1 over x to the p, it's going to be convergent when the exponent of p is greater than 1, and it's going to be divergent when the exponent of p is going to be less than or equal to 1. So we'll refer to this little theorem. All right, the first example wants us to determine whether this integral is convergent or divergent. So we're going to apply definition part A, since the limit is constant on the bottom and infinity on the top. So we can rewrite this as the limit as t approaches infinity of the integral of 3 to t. And I'm going to rewrite this as x minus 2 to the negative 3 halves, just for the sake of integrating. It makes it easier to integrate. If you find the antiderivative, you'll see that it's going to be negative 2x. This is going to become negative 2 over radical x minus 2 will be the antiderivative. And we're still taking the limit as t approaches infinity from 3 to t. All right, and then this can be rewritten as negative 2 over, actually the limit should go first. Negative 2 over radical t minus 2 minus negative 2 over, if you substitute 3, you're just going to get radical 1. And then these two negatives become positive. So this is going to just become plus 2. And then if you substitute infinity into t, this is going to be infinity in the denominator, which this will become 0. So your final answer is just 2, which means it is convergent. All right, let's look at the second problem. Example number 32 says determine whether the integral is convergent or divergent. Same directions, evaluate it if it is convergent. So once again, we're going to apply definition 1, part A again, because the constant is the lower limit. So this can be written as the limit as t approaches infinity of 2 to t e to the negative 5p dp. So to find the antiderivative, that would simply be negative 1/5 e to the negative 5p 2 to t, limit as t approaches infinity, which would then become the limit as t approaches infinity of negative 1/5. I'm going to write this as e to the 5t in the denominator, since the negative exponent will move that to the denominator. And then minus negative 1/5. And this would be e to the negative 10. So the two negatives become plus again, same as before. If you substitute infinity into t, the denominator is going to approach infinity, which means you have negative 1 over infinity, which approaches 0. So our final answer is going to be convergent once again, and it's going to converge to 1/5 e to the negative 10th. So that is convergent because the limit exists. All right, the next example, we're going to apply the same definition once again. So this is going to look like this. The limit as t approaches infinity from 0 to t, x squared, 1 plus x cubed dx. We're going to do the u substitution to be 1 plus x cubed, which means du will be 3x squared dx, which can be rewritten as 1/3 du equals x squared dx. And now we can substitute this part out and replace it with 1/3 du. So if you rewrite the integral, it's going to look like this. You have 1/3, and then you have u to the negative 1/2 du. All right. So that's what we have so far. All right, and then taking the antiderivative would give us, let's see, positive 1/2, so that's going to be 2/3 u to the 1/2. I'm going to go ahead and replace the u back in with 1 plus x cubed. We want to keep it in terms of x instead of u to make it easier on us. All right, so this is it. We should get this now. So now when you evaluate, you should get the limit as t approaches infinity of 2/3 1 plus t cubed minus 2/3. That's going to be just radical 1. And because when you substitute infinity into t, this entire term will approach infinity minus a constant is infinity. So in this case, the limit does not exist, which means it's divergent. All right, now we're going to move on to the comparison theorem. This theorem says that if you have two functions that are continuous, where the function f is greater than or equal to the function g, which are both positive, for x greater than or equal to a, then this integral is convergent. Now, if this integral is convergent, then g must also be convergent because g is bounded by f, and since if f is convergent, then this must be convergent. And vice versa, if g is divergent and it's bounded above by f, then that means that this integral must also be divergent. It's a little bit easier to think about if you look at this graphically. Let's say you have f and g. Notice that f is greater than g, and they're both positive. So imagine that f is convergent. If this function, the integral of this function is convergent, and it's greater than this one, then g must also converge. And vice versa, if g is divergent and it's bounded above by f, then that means f must also diverge. All right, so we're going to refer to this theorem for the next couple problems. So it says, use the comparison theorem to determine whether this integral is convergent or divergent. Well, let's look at the integrand. Notice that for the integrand, we know sine is bounded by 1 and negative 1. But if you square it, then it's going to be bounded above by 1. All right, and so we know that this will be the case. 1 over x to the 1/2 will be less than or equal to 1 plus sine squared of x over x to the 1/2, because this is a positive number, and if you add a positive number to 1, it's going to be bigger than 1, or equal to if this is 0, and the denominator is the same. So we know that this is bigger than or equal to that, and we know that this is divergent because p is less than 1. If we refer back to this theorem, if p is less than or equal to 1, then it's divergent, which it is for us. So the integral of 1 to infinity of 1 over x to the 1/2 dx is divergent with p equal to 1/2, and therefore the integral of this integrand will also have to be divergent by the comparison theorem, since this is greater than this and this one is divergent. Therefore, this must also diverge by the comparison theorem. So let's say that in words, thus, the integral from 1 to infinity of 1 plus sine squared x over radical x dx is also divergent by the comparison test. That's the conclusion. All right, so I'll just highlight also divergent by the comparison test. So it's very important that you say whether it's divergent or convergent, and you explain why. In this case, it's divergent because of the comparison test. We compared it to this function, which was less than or equal to this function, and since this one diverged, this one had to diverge by the comparison test. Okay, this last problem also wants us to use a comparison test. So it's given us an integral here. All right, so let's focus on the arctan function. The arctan function looks like this. There's an asymptote on the top and the bottom, and the graph looks something like this, where this asymptote is pi over 2, and this asymptote is negative pi over 2. So what we can say is that for x greater than or equal to 0, because our limit is greater than or equal to 0, as you can see by this, the function is bounded by pi over 2. So arctan of x is less than pi over 2, which is less than 2 as well. All right, and so what that means is that we can say this: arctan of x over 2 plus e to the x, that's going to be less than 2 over 2 plus e to the x. And because if the denominator is bigger, that means overall this fraction will be smaller than this fraction. So we know that this is bigger than this, because when you add 2 to the denominator, it makes the overall fraction smaller. So this is bigger than this. We can conclude that, which is the same thing as 2 to the e to the negative x if you rewrite that. So now, if we can show that this integral is convergent, and since it's bigger than this function, therefore by the comparison test, this integral must also be convergent. So our job is to show that this is convergent. Let's see if we can do that so that we can apply the comparison test. So let's rewrite this as the limit as t approaches infinity, 0 to t, 2e to the negative x dx, which is the same thing as that's going to be negative 2e to the negative x, 0 to t. Substituting t will give us negative 2e to the t. I'm just rewriting it in the denominator because of the negative exponent, which you're allowed to do, minus negative 2e to the 0, which is just 1. Double negative becomes positive. And notice that if you plug in infinity into t, you're going to have negative 2 over infinity, which approaches 0. So this entire term becomes 0, so your final answer is 2, which means it converges, which means it's convergent. And that's exactly what we needed. Because the integral of this function is convergent, and it's bigger than the integral of this function, by the comparison test, the original function must also be convergent. So let's write that. I'll write that here. Thus, the integral from 0 to infinity of arctan x over 2 plus e to the x dx is also convergent by the comparison test. And that concludes this section.